but this is something different. And this is something in which GIS and statistics both are used parallelly. Okay, so this case study is on life expectancy of Mumbai creeks. So as you know, there are three major creeks in Mumbai: Thane, Malad, and Manori. Thane is the biggest one. Malad and Manori are smaller than Thane, but all three are considered to be the major creeks of Mumbai, which provides ecosystem services to the urban areas of Mumbai. Now, what we have tried to do here is that we have published one paper also. You can see our impact of urbanization on creeks of Mumbai, India, a geospatial assessment approach. Here, Jaideep and me both were there. Jaideep just now delivered the lecture, and we have published it in January 2020. It is in the Journal of Coastal Conservation. So what we have tried to establish here is that you can see the base map of the study area. This is Maharashtra, and then this particular Mumbai region is the study area. So this is Thane Creek, this is Malad Creek, and this is Manori Creek. So what's happening here is that there are a lot of development on the edges of the creek. Okay, lot of development. And because of this development on the creek, they are discharging sewage in that. Okay, now Jaideep just now brief you regarding the problems which can occur if you discharge sewage in a creek ecosystem. Right, it will do siltation, as well as it will provide nutrients in the system, which will lead to eutrophication, as well as of course mangroves growth also be there. But ultimately, what will happen is that over the course of time, these creeks will get clogged. Okay, these creeks will get clogged, and proper ecosystem functioning of the creeks will not be there. So what we have done is that we have carried out one life expectancy analysis. In that, what we have done is that suppose if the same rate sewage discharge is being continuous to be in the creeks, we are discharging sewage continuously in the creek, what will be the life expectancy? After how much year this width of the creek will get clogged, and it will become a part of the land. That is what we are trying to work out using remote sensing and GIS. So as usual, the first step is preparation of base map, which you know that we have prepared. Then this is the methodology we have followed. We have collected data of various satellites, right? Then we have carried out ground truthing also. Then we have done image analysis, that is LULC, and then we have done accuracy assessment. And finally, we have done change detection and life expectancy analysis. That what will be the life of these creeks, how long these creeks will be in the form as it is in the present day. Okay, like that we have done. So this is the false color composite of the study area. As you can see here, this image is of 1972. This image is of 1994, and this is of 2016. Okay, because we have to see what is the change that has been occurred in that. And these are the three creeks. This is Thane Creek, this is Manori, and this is Malad. Okay, and also we have also done some ground truthing on that, because this area is highly accessible. We could go in this area, and we have done ground truthing on that for to see how our land use rent cover analysis has been carried out, the how much accuracy we could able to obtain. Okay, so these are the first color composite area of the three years: 1972, this one, 1994, and 2016. And then of course, in second step, what we do always is preparation of land use land cover map. So I hope this you know very well now how we would have carried out land use land cover analysis. So here you can see that we have divided the creek ecosystem in nine different classes, right from agriculture, barren land, built up, mangrove, mudflat, salt pen, beach, vegetation, and water bodies, different water bodies. Okay, so here you can see is that most of the time here are these creeks are blessed with mangroves, which is a good ecosystem service provider. Mangroves provide good ecosystem services to the nearby areas. But at the same time, we have to keep in mind that if this mangroves keeps increasing, one day the creek will get closed. Okay, creek will get closed. So we have to see what will be the life expectancy of that, and if it is reducing significantly, what we can do to stop the same. Okay, so this is the second step. We have carried out land use land cover analysis, and then as usual we have carried out the inventory also. So you can see that from 72 to 2016, the built up was around 21%, but now it is around 29%. So 8 to 10% increase in the built up area. Okay, and as usual, initially mud floods were more. Mud floods means the area near the creeks. Okay, area near the creek, mud flood or salt pan. You can see here it were more, but now it is decreased. Salt pans also decreased where the visible white sand is seen, that is called salt pans. Okay, that is also decreased. And some portion of beach areas also decrease because built up is increasing. Now with these three things, FCC, land use, land cover, and inventory, we have tried to see the change in the shoreline. Okay, yesterday also I showed you one case study in which we have divided the whole beach length in different 1 kilometer by 1 kilometer snippets, and in each 1 kilometer by 1 kilometer square box, we have tried to see whether there is accretion or erosion. But in this case, because we know that this area is fully developed, you can see this is development only. All these which is you are seeing with gray color, it is development. So all these people are discharging sewage in the creek only, and slowly what is happening, that sedimentation is happening, and it is slowly closing the mouth of the creek. Now if you see, this line is showing the shoreline of 1972, green line is showing the shoreline of 1994, and the white line is showing the shoreline of 2016. You see here, it was here in 1972. You see the yellow line. Then again, mangroves and grown. This is decrease, and again it has grown and this is decrease. If it continues, one day will come there when the creek will be like this, which is not good. Which is not good. It should have a certain limit. Of course, mangrove has various benefits to the ecosystem, but not at the cost of losing the creek. Okay, not at the cost of losing the creek. So this we have to see. Now you know that we have created these three things. This is for Thane Creek. Similarly, we have created for Malar Creek also. You can see the three lines. And similarly, we have created for the Manori Creek also, these three lines. Now, how I should proceed to see the life expectancy? So what I can do is that instead of snippets, I can check the width of the creek, which has been changed at various locations. Okay, at various locations. And then I can perform one statistical analysis called regression analysis, in which I can see what is the correlation between the year and the decrease or increase in width of the creek. Okay, so what we have done is that first we have taken one length here for all three years, that is 2016, 1994 and 1972. For all 3 years we have taken, and we have taken A, B, C, D, E, F, G, H, I, J up to this point. And for all three, we have plotted the width. On A point, how much was the width in 1972 and how much it is. And you can see the pattern very well in all years, the width is decreased only. Okay, width is decreased only. Why? Because there is development and they are discharging sewage. It is leading to sedimentation and nutrient, and that is leading to more formation of mud flood and salt man, and subsequent growth of mangroves. Okay, this is for Thane Creek. And then we have created this uh, linear regression equation for all the profile, that is A, B, C up to K. We have determined R square. R square is called as coefficient of determination. And this is the existing width of the channel, 8871 meters, almost 8 kilometers. And then if it continues in 2025, the width will be reduced to this. And in 2050, it will be reduced by 50 meters almost. Sorry, 400 meters, which is a big number. And similarly, at the mouth, that is the point number K, where it is going. Here, see, it is 93 meter now, and it will reduce to 30 meters. So you can see the width will be reduced like anything if the same sewage discharge continues. Okay. Similarly, we have done same reduction in width analysis for Malar Creek also. You can see your point A, B, C, D, E. In this case also, the average width is always reducing only. And again, we have performed one linear regression analysis on the same. And we have, using this equation, we have predicted the width in 2025 and 2050. Okay, and of course it is an alarming situation because one day it will get low. Similar analysis we have done for Manori Creek. In this case also, we have taken some snippets like A, B, C, D, E, F, and we have tried to see the reduction in width. So you can see here that width is reducing in all the years. Okay, so again we have carried out for this one also that if the same pattern continues, what will be the width in 2025 and what will be the width in 2050. And of course, in all cases, we are getting similar trend where width is getting reduced. Okay, so this was a small case study in which regression analysis was used to see the change. One second. So to see the change in width of a creek. But why I showed you this, I want to give you another perspective where this reflectance related properties are only used when I was seeing remote sensing GIS. You can see here. Reflectance related properties are only used when I was seeing remote sensing GIS. For the other ones, we have used our own GIS tool by digitizing the shoreline of the creek on our own. So this is also a one of the perspective where you can work out the life expectancy of a creek using remote sensing GIS. Okay, here I'm not concerning with the amount of pollution in that case study Jaideep has already showed you, and one more I'll be showing you anyway. So I'm not concerning to that. I'm concerning to that because of that what will be the change in the land environment and so significantly to the reduction in the width of the creek. Okay, so with this small case study is also over. We'll move to the second case study. But before that, if you have any doubt, I would like to uh, I'll be happy to clarify. This research paper also I'll share with you. I'm preparing one single PDF of all the 5 days. I'll share with you today itself apart from recordings. Before that, any doubt? Otherwise, we'll move to the next case study. Anyone? Okay, so if no further doubts, I'll share my second case study in which I'll show you how the remote sensing can be used to give the boundary condition. Okay, you have seen that Jaideep has shown you how the reflectance can be used to see the sea surface salinity as well as sea surface temperature as well as sea dome, that is color dissolved organic matter. All those things he has shown. But you have to keep in mind that sometimes we have to do the simulations. Okay, we have to do the simulation, and I told you already that the one of the main crux in EIA is how we can predict alternate scenarios, like what will be the scenario in 2020, what will be the scenario in 2025, and so on. So with that intention, I'll show you one more study. It is in Malad Creek only, but it is from a water quality and hydrodynamic simulation perspective. So I'll show you, and I will also show you a finer class animation of the water quality which you can do. Okay, but you have to keep in mind that I'm only showing you the interface of remote sensing. Okay, modeling is not our concern, that I've already told you that you have to do, but in that modeling activity, whatever you will be requiring from remote sensing perspective, that anyway we will deliver to you. We have delivered already in last 4 days, but that you have to keep in mind that is the interface of that. Okay, 1 minute. Okay, so my slides are visible again in slide mode. Any one of you?
Yes, sir.
Yes, sir.
Yeah.
Yes, sir. It is clear.
Okay, great, great. So now I will show you one case study in which remote sensing is only used to generate the boundary condition as well as the various hydrodynamic feature. But for water quality, simulations are used. Okay, in simulation, we have used Mike HD. I showed you on first day, second day in water environment that Mike HD is one of the versatile water quality simulation and modeling software. And I also told you that last day I'll be showing you one case study related to that. So that I'm showing you now how we can do simulation and we can generate animations to make the decision out of it. Okay. Now the title of our work was Hydrodynamic and Water Quality Simulations of Mallard Creek regarding EIA of WWTF at Mallard Zone of MSDP Stage 2. Here WWTF means not that fighting wala WWF, it is wastewater treatment facility. Okay, wastewater treatment facility at MSDP. MSDP means Mumbai Sewage Development Plan. Okay, Mumbai Sewage Development Plan. Stage 2. It was in various stages. In that, we were doing some study. So our task was, if this is a creek, okay, this is a creek. Our task was to see if I set up a treatment plant here. If I set up a treatment plant here you can see WWTF. If I set up a treatment plant here and if I discharge the treated water here, what will be the impact of the treated water in the creek? One thing. Second thing, there were three proposed outlets. Okay, there were three proposed outlets. Which outlet will have least impact on environment on the creek if I give that outlet? So here now I want you to understand something. What all things you are seeing in red dot are drains. Drain D1, D2, D3, D4, D5, these are drains. That means they are flowing from somewhere and they are meeting into the Mallard Creek. Okay, they are coming and meeting into the Mallard Creek. These are drains. And what all yellow points you are seeing, this we have taken samples for giving input to the modeling activity. Okay, as Jaideep said, and as I am also conveying to you, some 5 to 10% of laboratory work will always be required. We should not completely rely on remote sensing. Okay, it should only be used to reduce our field work and which it does. It always reduce our field work like anything. We don't need to do more. Okay, so this M1, M2, M3, M4 and M5 and up to M8 are my sampling points. Okay, these are my sampling points and these red dots are drain. So my job is to see these drains are also contributing, right? And if there is a treatment plant, it will treat the water and it will also discharge the waste here. Then what will be the impact? Okay, now what is the role of remote sensing here? The role of remote sensing here, the biggest role of remote sensing here is to give the proper boundary condition. Okay, proper boundary condition. You yourself think if you are doing some simulation and if the model of that simulation does not know its boundary, where it will stop and simulate? Nowhere, right? So this all whatever you are seeing, this is a boundary condition which you have given using remote sensing and GIS. And this is the map of bathymetry of the study area. Someone was asking us few days before whether with remote sensing we can measure the depth or not. So I would like to again convey that for bathymetry, instruments are there and using that instruments only we need to measure. So whatever this area you are seeing, the orange area, it is the above 0 point, means that is land. And from here the creek is starting, the yellow one. You can see -1 to 0, then -2 to -1, -3 to -2, like that. And this is the deepest part where 5 to 6 meter of creek width is there. So bathymetry plus the normal boundary, these both are required to give the input in the water quality simulation model, which in our case we have used Mike HD. Okay, we use Mike HD. Now, apart from that, we need to see the tidal elevation also at the mouth of the Mallard Creek, like how this our tidal waves are varying. So you can see here that initially that variation will be less. That's why the width is less. Then afterwards variation will be high. Okay, afterwards variation will be high. So we have to simulate and see for all these situations when the tide is low and when the tide is high. Okay. And this is at the mouth of the Mallard Creek, and this is at the Mouth means from where the water will enter. This is the, sorry, this is the mouth and this is the tip of the creek. Okay. Now, one thing before I go ahead, one thing I would like to explain you is that I hope you all know regarding the full moon and no moon. Okay, it is a cycle of 15 days, right? I want to explain one concept to you so that it will be easy for you to understand the further things. Okay. Uh, let's say this is a cycle of 15 days. 15 days. And let's say this is another cycle of 15 days. Okay, completing a 1 month. Completing a 1 month. Now you divide this in 3 parts. 3 days, 6 days, and another set of 6 days. Okay. Then again, 3 days, 6 days, and another of 6 days. Okay. Now these are two cycles. Suppose this is full moon. This is full moon. Okay, this is full moon. So from full moon to no moon, I can divide the type of tides in 3 parts. When it is full moon to no moon, the initial 3 days will be highest of high tide. Okay, highest of high tide and lowest of low tide, means high tide also will be high and low tide will also be low. And the next 6 days, it will be springtime. Okay, spring, high tide, spring, low tide. And when it reaches to no moon, it will be neap. It is called as neap, NEAP. Neap high tide and neap low tide. So in neap, naturally the high tide of neap will be lower than the high tide of spring, and the high tide of spring will be lower than the high tide of highest spring, highest of high tide. Okay, during full moon. So you have to keep in mind that it runs in series of 3 days, 3, 6, 6. Highest of high tide, then spring high tide, spring low tide, and neap high tide, neap low tide. In our case, I am not considering highest of high tide because many times it is not that significant. So I'll be showing you the tidal variations in springtime and neap time. Okay, so first I told you already, first we have to do hydrodynamic simulation for depth of water for present condition. Okay, so this we did in 2017. So here present condition refers to 2017. So first I am showing you a map of neap high tide. Here you can see that the water depth is 5 meter, then 4 to 5 meter, and like this below 1. Then neap low tide. Naturally, when it is low tide, water will be nearer to creek. Toward the center of the creek, this area will be empty. That is the reason where you can feel the wetness in sand, but no water. Okay, so this is neap high tide. This is no neap low tide. Now this one is spring high tide. I told you na the next 6 days is spring high tide, in which water will be high, but it will be slightly 0.5 to 1 meter higher than the neap high tide. You can see here that it is slightly far, but in spring it is slightly going closer to the boundary because this is springtime. The gravitation pull of the moon is in gravitation pull is increasing. This is spring high tide and this is spring low tide. And since it is going high, again the low will go more low, right? Because of the forces, different forces. So this is water depth. Now, what our task was to, based on these 8 locations, this M1, M2, M3 and M8, we have determined BOD, COD, no sorry, BOD, DO and FC. Okay, biochemical oxygen demand, dissolved oxygen and FC. So now we will see all these 3. So here in this case, this is BOD of present condition, which was 2017. This is in neap high tide. So you can see that these areas are the areas where BOD is above 70 milligram per liter, and this is area where it is 30 to 70 and below that. Now this is BOD in present condition in neap season, low tide. This is BOD in spring high tide. Now you yourself observe when it is neap high tide, still BOD is high because the water is less. But when it becomes spring high tide, BOD is in the range of 30 to 70 because water is more. So dilution will be more and BOD will be low. And this is spring low tide in present condition. Okay. Then this is DO, dissolved oxygen. So in neap high tide, most of the reason was DO was less than 1 milligram per liter. This is neap low tide. Again, it is getting below 1 milligram per liter. This is spring high tide, slight improvement. And then this is spring low tide. When it is low tide, you can see that DO has also decreased significantly because there is no water which will provide the fresh oxygen to the system. Now this is fecal FC, fecal coliform. As I told you earlier, nearby developments are there and the human waste also they are discharging in that. So this is fecal coliform in neap high tide, fecal coliform in neap low tide. You can see full of FC above 10 to the power 5. This is spring high tide because water is more, it is slightly increased, slightly improved. And this is spring low tide when there is lowest water quantity available to dilute this. Okay, so this is BOD, DO and FC in present condition. Okay, now my job is to see which outlet will be best. Okay, I told you already the location of outlet option in Malad Creek for future scenario. So these are the three options given to me. That out of these three options, outlet 1, outlet 2 and outlet 3, you choose which one will have least impact on the creek in terms of DOD, BOD, DO and fecal coliform. Okay, so we have generated two scenarios, one for 2034 and one for 2050. Okay, so again, we have given a future scenario 2034 in which what we have done is that we have assumed that whatever values we are getting now, 60% of that is treated. Okay, with that 60%, we have again run the same simulation, but this time the quality of the water is improved. So you can see here that the BOD is not that high. It is not at all going above 70 anywhere. Okay, you can see here that not at all going anywhere 70, which was going in the present situation. So similarly, neap high tide, neap low tide. Here also, even though water is low, at least 3 to 10 milligram per liter stretches are there. Then spring high tide, this is more improvement. Spring low tide. Okay, this is for BOD for future scenario 2034. Now this is DO for 2034. DO also you can see here that now the area which is DO at least between 3 to 4 milligram per liter is increasing because I am assuming that 60% is treated and I have given that input in the model. This is neap low tide, spring high tide. Again it is much improved and spring low tide. Okay, even if it is low tide, the area in which DO is less than 1 are very less. You can see here. Now we'll come to the fecal coliform. So this is future condition 2034. Now at least this area is reduced. Earlier this area was coming up to this point. So when it is between 100 to 1000, this area is there, which is neap high tide, neap low tide, fecal coliform, spring high tide, and spring low tide. Okay, so like that I could see if I do 60% treatment, what it will work. Now comes 2050. In 2050, I'm assuming that at least 90% of the water will get treated. Okay, 90% treatment we are achieving, only 10% we are discharging without treatment. Okay. So in that case, now again you see this area is increasing again, this one 10 to 30 because I have given that much. So this is for neap high tide for BOD 2050, neap low tide BOD 2050, spring high tide BOD 2050 and spring low tide BOD 2050. So here you can see that not at all this thick maroon color is there. Means nowhere it has gone above 70. Then DO for future scenario 2050, neap high tide, neap low tide, again spring high tide, spring low tide. Okay, this is for future scenario. And lastly, we will see the fecal coliforms in which again we'll start with neap high tide. Okay, 2050, still it is there, but again this area is increasing. This area is increasing where fecal coliforms are less. Neap low tide, spring high tide, spring low tide. Okay. So with this, I end this case study, but I want to show you one simulation, like how exactly it goes. So this is future scenario for 2034 and it will look like this. So I hope you are able to see the animation moving. Can anyone just
Yes, sir.
Yes, sir.
Yeah,
It's
okay. Okay, great. Now, what I want you, where I would like to draw your attention is that this is for 15 days. I told you na between full moon and no moon. So you can see here that it will slowly show us that in that 15 days, what will be the BOD range between high tide and low tide, specifically in neap high tide, neap low tide, spring high tide, and spring low tide. This is for BOD. So it is showing how it will move when there is high tide and low tide. This is for BOD 2034. And then this is for DO 2034. So you can see when water is more, the high DO areas are increasing in between. Okay, this the blue color, you can very well see that. Okay, and similarly, this is for fecal coliform 2034. When more water is there, the highest fecal coliform areas are reducing. And keep in mind that this is for the 15 days region. In that only we have to decide it. And similarly, then we will see for the 2050. Now, when we are going to 2050, I told you that we are assuming more treatment are there. So you can see that blue area is going up to the top where I'm moving my cursor. All right. Blue area is going up to the top, up to this point, which was not going in 2034. Okay. Similarly, DO in 2050. DO in 2050. That is also going up to the here high regions. And in 2050 fecal coliform. So even you can see that in some reason it is going below 100 also. You will see it will pop up that color. I'll show you again. Wait. You will see here. You see here that that color is coming. That means it is below 100. Okay. Okay. So and similarly we can do one simulation for water depth also. So this is how water depth will increase or decrease in the region. This blue color below 1 meter, this is above 5 meter when there is high tide and when there is low tide. Okay, now there is one term called fast forward flow. Fast forward flow means it is also called as a dream scenario. It is also called as dream scenario when 100% of the wastewater is getting treated. I started with 60, then 90. Then there will be a scenario when I'm able to treat all 100%. Then what will be the scenario in that case? So you can see in that case, it is all blue because I have treated all 100% I have treated. So no color pertaining to 30 between 70 and above 70. All right. POD. Similarly, DON fast forward flow, it will be, you can see up to 1 to 2 is always there. Below 1, nowhere it is going. Only slight area it is going in fast forward flow. And again, fecal coliform in fast forward flow. So here also this dark color where this is 10 raised to the power 5 was there, it is not there, and blue are there where only it is 100 to 1000. This is called a fast forward flow. Okay. So you can ask me any doubts. Just I'll make a call. Hello? Is there any doubt? And then when I say doubt, please keep in mind that you have to ask me from the interface of remote sensing. Yes, other things I can very well clear you, but that is not in the scope of this. That's why that you only have to do other things. Uh, Anyone? Any doubt or any clarification? Okay, so we will meet around 1:30 to 2. I'll put on the group. There will be 1 hour lecture by Engineer Shrawant on coastal regulation zone. And last lecture I will take for the job opportunities that you all should attend. I will give you the list of consultants who are working in EIA. I will also show you some of the resources which you can use for getting job in this field. Yeah, did you consider about global warming and increasing sea level? This simulation is used for dredging too. Yes, yes, we can use this simulation for dredging also. And yes, we have considered increasing sea level. Global warming we have not used because it is not one of the forcing function in this. Okay, sea level we have considered, and with that sea level only we have done that simulations. Any further doubts? Welcome. So, okay then, most likely we will meet at 2 only because we have some other administrative work in between. And but you should attend the last 2 sessions. I'll be sharing you the list of consultants who are working in EIA. What are the qualifications which you require to work in EIA? How to approach, and what are the function areas which are prevalent in EIA, which you can choose now itself and you can start working on that. Okay, so and after that we will have a feedback session. I request all of you to be seated in such a position that you can on your video camera at least for 5 minutes, so that we can take a screenshot and I can forward this report for Skill India initiative because this program is under skill development programs. Okay, okay. Thank you all.